Okay, so now we're going to look at the geometric series. And here I have the definition of the geometric series. It's the sum from n equals 0 to infinity of a times r to the nth. A is the first term in the series, and r is the common ratio of this geometric sequence. And when you sum up all the terms of this geometric sequence, you get the geometric series. And let's see, the ratio is r. And here's a theorem for the convergence of a geometric series. Um, if you take a look over here, here we have, this would be the nth term, or the nth partial sum. Sorry, this would be the nth partial sum of a geometric series. And if you go ahead and multiply this nth partial sum by r, you get r multiplied by Sn, and that would equal, well, this term when you multiply it by r, you get a times r. This term when you multiply it by r, you'd get a times r squared. This term when you multiply it by r, you get a times r to the cube. And then you continue on like that, all the way up till this term, which would be a times r. And then when you multiply r to the nth by r, you get r to the n plus 1. So you get this when you multiply r by the nth term. And what we're going to do now is we're going to go ahead and we're going to subtract these two equations. So on the left side, I'm going to have the subtraction of these two terms. It's going to be Sn minus r times Sn. Let's see what that equals. Well, a is going to be the first term, a. And then I'm going to have plus a times r, and I'm going to have these terms. But notice I'm subtracting off these terms. So this a times r is going to be subtracted, and they're going to cancel each other out. So these terms are going to cancel when I do the subtraction. These terms are going to cancel also, because this is going to be positive ar squared, and I'm going to subtract this one because I'm subtracting this equation. This will be negative ar squared. They cancel out. The next term would cancel this term, and I'd go all the way, and let me see, I'd have a term to cancel this one too. The term that comes right before this term is this exact same term here. So the term that comes right before this one is ar to the nth. So that would cancel the ar to the nth. And this term wouldn't have anything to cancel. So you'd find out, you'd see here that this would be equal to a minus a times r to the n plus 1 power. These are the only terms that would remain when you did that subtraction. Now, once we have that subtraction, I see over here that if I factor out Sn, I'll be left with, oops, let's see. If I factor out Sn, like I said, if I factor out Sn, I'd be left here with, well, if I factor Sn out of this term, I'll be left with 1, minus, if I factor Sn out of this one, it'll just be r. So on that side, I'll have Sn times 1 minus r. And out of this side, I can factor out an a. Here I have a in both terms. So if I factor out an a, I'll get 1 minus r to the n plus 1 power. All right, so now I have a way I can solve for Sn. I can find the sum here. I can find the nth partial sum, Sn, by dividing both sides by 1 minus r. So I get that Sn, the nth partial sum, is equal to a over 1 minus r multiplied by 1 minus r to the n plus 1 power. So this would be a way of describing the nth partial sum. If I know r, a if I know R and A, I can find the nth partial sum by just plugging n in. I can find the fifth partial sum by just plugging in a 5. All right, so this is the nth partial sum. Now let's see if this, what makes this converge. All right, so the sequence of partial sums would be this sequence that contains these terms, which are the nth partial sums. So it would be this sequence here. And what we want to do is we want to see what causes this sequence to converge. So we want to see what makes this sequence have a finite limit. So let's go ahead and take the limit here. We want to see if this converges. The limit as n approaches infinity of the terms of this sequence of partial sums, Sn, is going to equal, well, this is going to be the limit of this thing as n approaches infinity, which is a times, or a divided by 1 minus r multiplied by 1 minus r to the n plus 1 power. Alright, so I'm taking this limit. I see here that this limit, none of this involves n at all, so I can bring it out of the limit. And this will be the limit as n approaches infinity of 1 plus, or 1 minus, not plus, 1 minus 1 minus r to the n plus 1 power. Alright, so this limit now, well, as this limit, the limit of 1 as n goes to infinity is just 1. That's a constant. The limit of a constant is a constant. So what I'm really concerned with is the limit of r to the n plus 1 as n goes to infinity. So let's see. Let's focus on that bit. This limit depends on the value of r. Now, let me erase this. Because this is a ratio, there's a numerator and a denominator. And if this fraction is between 0 and 1, for instance, let's say r is between 0 and 1. Well, if r is between 0 and 1, if the absolute value of r is between 0 and 1, then what you have is the case that when you raise this to powers, it becomes smaller and smaller and smaller. So any number that fits this description, any number whose absolute value is between 0 and 1. As you take consecutive powers, the number becomes smaller. You're finding fractions of that original number. So, um, this condition is the condition we need for this limit to converge. Otherwise, if the absolute value of r is bigger than 1, then you get the case where you're multiplying a number that's greater than 1 um, by itself multiple times, so the number gets larger and larger and larger, and this thing actually blows up. So this is the necessary condition for this limit to exist and for this sequence to converge. So it turns out that for geometric series, you can tell about convergence just by knowing the value of r. If the value of r is between, if the absolute value of r is between 0 and 1, then the limit will converge, and you will get that the series converges. And that's theorem 9.6 here. Theorem 9.6 says that this limit, not only will the series converge, but it will converge to this sum, a over 1 minus r, which is what we see over here. Um, as long as this condition is met, then this limit is just a over 1 minus r. So that's theorem 9.6. Let's take a look at an example. All right, let's go down here. An example. All right, so we're going to determine the convergence or divergence of, let's see, what we're going to look at is this one, the sum from n equals 0 to infinity of, let's say, uh, 1/3 to the power of n. Well, let's see. In this case, this is very direct. This is very straightforward. If I let a equal 1 and I let r equal 1/3, then this can be written as the sum from n equals 0 to infinity, and 1/3 is what I'm calling r to the nth power, and a is the number 1, so this is multiplied by 1, and here I have a times r to the nth, a times r to the nth. So basically what I have here is I have a geometric series. This geometric series has a as 1 and is multiplied by r to the n, and by this theorem over here, theorem 9.6, this converges because r is less than 1 but greater than 0. So because the absolute value of r is between 0 and 1, this series converges, and it actually converges to, let's see, a, which is 1, over 1 minus r, which is 1 minus 1/3. So that gives us, let's see, that's 1 over 1 minus 1/3 is 2/3. And when you find this fraction, it becomes 3/2. You flip and multiply. So not only does this geometric sequence converge, it converges to 3 over 2. All right, let's see. All right, well, that is the discussion of geometric series. Um, what we really need is this theorem here to determine convergence, and all you have to do is look for the value of r. If the value of r is between 0 and 1, then it converges. If r is greater than or equal to 1, if the absolute value of r is greater than or equal to 1, then it diverges.